I'm going to go through and discuss week 12 worksheet, which is using this quantum tunneling and wave packet simulation. So I've gone in, right now everything's on the default settings except I have shown the reflection and transmission probabilities, which are shown here, and I've switched to a plane wave. Right now it is paused. So the first question is whether it is a standing wave or a traveling wave. And the key is that you can see over here, it is traveling to the right. And so this would be a traveling wave, which is what a plane wave is. So notice that here you do in fact have the amplitude increasing and decreasing. That's due to reflection. But fundamentally, this would be a traveling wave to the right, which then is partially reflected. Second question is the energy higher or lower than the barrier? And again, on the default setting, your barrier is shown here in purple. The green line is your energy, so this is higher. Part of the way, another way you can tell this is it's still oscillating. It's still sinusoidal in the middle. So that tells you that you have to have an energy that's higher than the barrier, or else you would have exponential decay. The next question is whether or not the energy of the particle is the same on the left and right of the barrier. This is hugely important and one that students primarily get wrong. Let's pause this really quick. So now we can try to look, and one of the ways to determine this is to think about the wavelength, the apparent wavelength of the particle. And you can see here that the wavelength stretches, there's not actually a way to measure this, but from about halfway to the next mark, so kind of 1.5 boxes roughly. And you can see over here that it's also about 1.5 boxes. Again, a little bit difficult to tell given that we don't have a way of measuring it exactly. Another way to think about it is looking up here. That green band is the energy of the plane wave. It is always staying the same. So I can't stress this enough. This is a very, very common misconception that even after doing the simulation and doing this activity, I find many students have this wrong. The energy of the particle is the same on the left and the right. Now, you might say, but the amplitude is different. And we've learned that the amplitude typically had to do with like kinetic energy changing. That's not what's happening here. The amplitude is different because we have some transmitted and some reflected. Most of it's transmitted, but some of it is reflected, so we see that reflecting wave interfering with the incident wave. But it's really critical to understand that the energy of the particle is the same on the left and the right. So what this wave function looks like is we have 3 regions, and it's actually sinusoidal in each of the 3. So you do in fact have a sinusoidal region here. You have a sinusoidal region in the barrier, though that's a little difficult to tell. But here you can again see it's kind of sinusoidal. So everywhere it's in fact sinusoidal. And it's continuous. Right? Our total wave function here, notice that we're looking at the sum, not at the separate pieces, that it is continuous, and it looks like it's continuous in the first derivative as well. So the transmission and reflection probabilities, we have a very small reflection probability and a very high transmission probability. And one of the ways that you can think about this is that we do see some oscillations on the left, but in general, we can see that really it looks like almost the same amplitude that we have on the left, though there are variations, is on the right. So that would be almost all of it being transmitted. So that's the first part. Now, the second thing we do is we go into configure energy and we set the average total energy to be 0.3. I apply and I close. We immediately see that there's a change here. So let's think through this. So the first question is it a plane wave, or sorry, is it a traveling wave or a standing wave? Now, again, we see very clearly here that it's traveling to the right. Now, you might say that this looks like it's a standing wave on the left. Now, the tricky part is here that it is in fact going to be, if you look here, my node is staying in the same place. So it's something similar to a standing wave on the left, and that's due to the fact that it's being reflected in this way with kind of a fixed point. But we clearly see here that there's a traveling wave. So we're still talking about a traveling wave, but where almost all of it is reflected. And we know that if you reflect a traveling wave back, then you do get a standing wave. So the second question, is the energy higher or lower? lower. We clearly see that green line lower. And notice now in the barrier, if I pause it, we have some sort of exponential decay occurring. So it's no longer sinusoidal here, it's exponential decay. And there's some places where it looks a little weird, and we in fact have both solutions of that exponential here, but it still is the solution to the differential equation where your energy is lower than the barrier. So next is the energy of the particle, the same on the left and the right. Now again, let's look, and you can see that here, again, it's a little bit tricky to tell. So we have one box, two box. So it's just about two boxes, but not exactly. And over here, it's again, two boxes, not exactly. Our wavelength hasn't changed. So the energy on the left and the energy on the right are the same. Again, a little bit difficult to measure. Notice here that again, it's really close. Let's see, 1, 2, little more than 2. And again, we see here, again, count 1, 2, and here 1, 2, a little more than 2. Our energy hasn't changed. Again, that green bar is the same on the left and the right. So please, please, please understand that the energy of the particle doesn't change as it quote unquote tunnels through the barrier. It's just a question of the probability. What does the real part of the wave function look like? Again, we have a sinusoidal function on the left, a sinusoidal function on the right, and then what's connecting them is actually an exponential decay. Now, it's not exactly an exponential. We kind of see some weird things like that happening on the shape. And again, it's a sum of one that's kind of exponentially decaying this way, but then one that's kind of would be growing. And you need both of those so that you can have your first derivative being continuous at both sides, the amplitude being continuous at both sides. Lastly, we see that the reflection probability is now 0.96, the transmission probability is 0.04. And so fundamentally you see that our maximum amplitude here is much, much, much bigger than what's happening there. And again, this really starts to look very much like a standing wave here. And we can think about this looking like a standing wave since, again, almost all of it is being reflected. And it's just a little bit coming through. So I'll pause here, and then the next video will continue this.